Good morning, everyone. I think we'll get started. We have probably some more people that are going to join, but we'll get us started on time. So my name's Carly Sawecki. I'm a senior project geologist at TriHydro, and I'd like to welcome everyone to our webinar series. The second webinar in our four-part series is called Deep Injection, Real Consequences, Permian Basin Lessons for Class 6 Wells. And this is part of our larger webinar series called Uncertainty to Delivery, Real World Lessons from Class 6 Projects. So we've gathered a bunch of speakers to talk about either their real world experience, or in this case with Dr. Katie Smyth, her research in the Permian. So I'll introduce our speaker. Our speaker today is Dr. Katie Smyth, and she's going to present on how her saltwater disposal research in the Permian informs risk, site selection, and monitoring strategies for Class 6 injection wells. And she'll focus on pressure management, fault reactivation, and wellbore integrity in this heavily developed basin. So before I officially introduce Katie, just a few housekeeping items. So just so you guys know, all the attendees are in listen only mode. So if you have any questions, you can use the question panel in your Teams menu, and we'll save a few minutes at the end of the Q&A, or at the end for Q&A after Katie's done presenting. And then if we don't get to your questions in the hour, we'll respond to you directly via email. And this webinar is being recorded, and the recording will be available just for folks who registered for the webinar. So, okay, now I'll introduce our speaker. So Dr. Katie Smyth, she's a research assistant at the University of Texas at Austin, and she's the principal investigator for the Center for Injection and Seismicity Research. This is a consortium focused on injection capacity and seismic hazard mitigation in the Permian Basin region. And she has a PhD in Earth Sciences from the University of Cambridge and bachelor's degrees in geology and chemistry from the University of Oklahoma. So excited, Katie, that you could join us today, and I will turn the presentation over to you.
Perfect. Thank you so much, Carly, for having me as part of the seminar series, which seems like a great series. Hopefully everything looks and sounds okay with my screen and audio. Someone ping me if not. So I'm really excited to be able to talk to you today, not about Class 6 injection specifically, but about what we can learn from the Permian Basin region. And I think that there are some important lessons that come out of our work in the Permian Basin. Because one of the big questions is, what does it look like to undertake an injection operation at scale, at the basin scale, at the regional scale, not just a couple of projects here or there, but what does it look like when we have overlapping interference, we have injection at multiple subsurface levels, and what can we learn? And the Permian Basin really provides the best opportunity to study this with a different type of fluid, Class 2 saltwater disposal. So I shall dive in here. So my role at UT Austin and at the Bureau of Economic Geology is to lead this Industrial Associates program called CSIR, the Center for Injection and Seismicity Research. And I was the only author on the title slide, but really everybody you see listed on the left is a co-author of this work, because I'm representing the work of this team with a broad range of expertise, from subsurface characterization to reservoir modeling to aerospace engineering, looking at deformation of the ground surface from satellite data, geomechanics, structural geology, seismic interpretation, and more. So a very broad range of expertise needed to build up this integrated understanding. In our group, we have sponsors, mainly Permian Basin operators, but some outside the Permian Basin, international super major oil and gas companies, midstream companies, which are tasked with water management, specifically managing and disposing of water, land and minerals companies who have an interest in what happens on their land and their acreage, and who have thoughts about whether that land is used for injection, and regulatory agencies. So the New Mexico and Texas regulators, which are the two states that the Permian Basin encompasses or is part of, are sponsors of our program as well. So we have this really diverse stakeholder group to kind of bring different expertise to bear on the work that we're showing here. And in our research group, we also have technical partners who provide high quality data for us. And this probably is relevant for Class 6 as well. Commercial companies like B3 Insight who aggregate and supply high quality injection data. So not just monthly injection, but daily rates and pressures. 3D seismic companies like Fairfield, subsurface data, passive seismic data from Nanometrics, so earthquake catalogs that are high resolution, better resolution or lower magnitude of completeness than what's publicly available. And then commercial providers of INSAR surface deformation data, and that is SatSense in this case. So what do we need to know and study when we want to understand the impacts of large-scale injection on the subsurface and surface environment? So the first thing I want to say is that this is not just a Class 6 question or a Class 2 question. Many energy extraction and storage operations involve injecting or removing fluids from the subsurface. And this means we need to understand how the subsurface responds to these changes. So even hydraulic fracturing is part of this. That's an injection operation, putting fluids in the ground, disposing of water, sequestering carbon, storing hydrogen, producing geothermal energy through enhanced methods, so drilling and hydraulically fracturing and flowing fluids to produce heat. All of those have the potential to change subsurface pressure and stress environments. And these changes in stress and pressure can lead to adverse impacts. Induced seismicity is one of those. And I'm showing on the right one of those conditions where you would see failure of a fault and seismogenesis, formation of an earthquake. So if you're familiar with a Moore circle or a Moore diagram, when we have our original unperturbed stress state and then we perturb our stresses, we can push that rock volume closer to failure. And in complementary nature to that, we might have unfaulted country rock that's relatively strong, but that rock becomes weaker when we have a fault. But some of those faults have some cohesion, they have some stickiness to them. There also might be a case where we have a weak fault. And so as these two things come together, our geology and our perturbation of the stress environment, we may be more and more likely to see earthquake rupture, seismogenesis. So what are some of the factors that we need to know and we study? I think of them as two things. One of them are these geologic things that impact how fluids and pressures migrate. So what do we need to know about the reservoir itself? Its depth, its thickness, the type of rock, how heterogeneous it is, are the porosity and permeability structures governing flow relatively predictable or heterogeneous? What's the compressibility of the system? Very important for what we come to understand as fluid buildup or pressure buildup, and therefore injection capacity. What do we have for in situ stresses? What are the magnitudes and orientations of stresses in the Earth's crust? What do we need to know about faults? Do we have them at all? What's their geometry, their extent? What type of rock are they in? How stable or slippable are they? And what's their potential for making earthquakes? And then importantly in Class 2, and even probably more importantly in Class 6 injection, what do we know about our confining units, our cap rock geology? What's the fracture gradient, and other characteristics? And then layered on that, we have another set of factors that in my group we don't spend a lot of time on, but they're important. These are anthropogenic things that represent hazard and risk. So what is the nature of the built environment? How likely is the ground to shake with an earthquake? Do we have a lot of legacy wellbores? Do we have proximity to aquifers? What are the existing oil and gas operations? And what are the threats to business interruption if we have an adverse event? So those are all things kind of on the anthropogenic side. So the Permian Basin we use as this laboratory to understand the impacts of large-scale injection, and there are several reasons for that. And I hope that you'll be, convinced with me that we can learn a lot of interesting things here. Some of the reasons why this is a great laboratory to study: we have hundreds of thousands, 265,000 documented legacy wells from a century of oil and gas production. We have tens of thousands of currently producing unconventional wells. We have 23 or 4 million barrels of water a day produced and 20 million barrels a day of water injected, which is an astronomical volume, something akin to an Olympic-sized swimming pool every minute or two. We have a very heterogeneous stress field, different sets of faults. We have a lot of earthquakes. We also have near surface issues, well blowouts from legacy wells, surface flows of effluent, etc. And then on top of that, we have the fact that this basin currently produces half of US oil and is responsible for some natural gas exports. So it's a really important local, national, global economic basin for production. So it really gives us this nice laboratory to study. I have way too many slides today and I won't get through all of them. And so I want to start with some of the key learnings here, and then I'll go through the science of how we get to these key learnings in the following slides to the degree that we can. So here are some of the main points that I'd like to get across throughout this talk. One, fault rupture and seismicity can be initiated at great distances from injection and at relatively small pore pressure changes. And there are a few things that have been shown to be higher risk in class 2 injection that are relevant here. Injection near basement, that crystalline rock that underpins the basins that we inject into. Injection near basement is problematic for seismicity. Injection into rocks with high diffusivity and a lot of heterogeneity is challenging because it's difficult to model pore pressure plumes in those types of systems. Systems with structural and geomechanical complexity, complexity in our stress fields, in our faulting environment are also higher risk. The second point that I'd like to get us to today is that site characterization is critical, but we have to pair it with adequate monitoring and mitigation strategies. So not all the faults that we see hosting large earthquakes can be easily characterized in 3D seismic data, even very good quality data. And so we need to have monitoring strategies in place to detect and kind of understand and aid in that site characterization, closing that loop between monitoring and characterization. And then early mitigation strategies might avoid project losses. I'll show you some of those project losses today. And of course, there have been cases of that in class 6 injection also. Legacy wells are a hidden risk, and that risk increases with overlapping and large-scale injection projects, and that too can be present at great distances from injection. Some of the compounding risk factors there are poor quality cap rock for containment loss, for example. And then we see that surface deformation serves as an early warning signal for containment loss in your injection operation. And so we'll get to these things. The way that I want to spend the next maximum 30 minutes or so, leaving time for questions, is to group this talk into 3 topics. I'll spend 10 minutes on each of these. First, I want to show you something that's slightly less relevant to class 6 injection, but frames the following 2 points, and that's what's happening in the Permian Basin that make it unique as a large-scale injection laboratory. And then I want to talk about deep injection related things. So injection near basement, fault rupture, and earthquakes, and what we can learn from that aspect of Permian Basin development. And then move to shallower strata and talk about a nearer surface thing. How do our reservoirs respond to injection into systems that don't have a lot of earthquakes, but have other risks like legacy wellbores? And what are the potential impacts on the subsurface and surface environment? Okay, so what's happening in the Permian Basin? There has been, as I said before, a century of production in this basin. So this is not a new, water production in the Permian is not a new thing. We have had water produced from conventional reservoirs, that's the dashed line in blue that you see here, for many decades. But it's really this unconventional produced water, the water produced with horizontal drilling and hydraulic fracturing, that's posed a problem. And you can see in the map on the right the footprint of those operations in the same color scheme. So this basin is made up of 2 main sub-basins, the Delaware and the Midland, where most of our unconventional production happens. And then it's surrounded by platforms the Central Basin platform is a basement chord uplifted platform, as well as the Northwest Shelf and the Eastern Shelf. And those structural traps are where we've had most of our conventional production historically. But you can see areas, much of the Midland Basin and parts of the Delaware Basin in concentrated areas where those conventional wells sit in the same footprint as unconventional wells. And so we have some overlapping legacy and modern operations. Now, I said that conventional production has not been an issue historically in terms of injection capacity, and that's because the water produced with those operations was re-injected into the same reservoirs it was produced from for enhanced oil recovery in a generally pressure balanced fashion with a voidage of 1. So it didn't increase the pressure really in the reservoir that we saw globally or at the regional basin scale. It's really the solid blue line, the unconventional produced water, that poses most of the challenge we see today. So the water is coming from the regions that you see on the left here and in the density that you see. This is now, these maps are shaded by water volume produced for every square mile block, conventional on the left and unconventional on the right. And you can see unconventional on the basins, conventional on the basin margins. Now, in both of the two subbasins, unconventional produced water far outweighs conventional produced water today, but given those overlapping operations I showed you on the last slide, the Midland Basin still has an appreciable amount of conventional produced water. Now, I won't spend too much time on this, but I wanted to show you kind of the fraction of the fluid produced and how much of that is made up by water in the map on the bottom right and in the plots on the top. So this shows water cut for all wells drilled in a square mile block, and for all of their production to date, what the fraction of the fluid produced is made up of water. And so areas that are dark red are anywhere from 80 to 100% water produced. Areas that are in blue are lower water cut, something like 20 to 40% or a bit lower in some cases. So you can see a great deal of geographic variability in our water cut across the basin. So now getting into the kind of class 6 parallel, and that's injection of this produced water that I just showed you on the previous slide from unconventional production mainly. And so injection in the Permian Basin really goes into two stratigraphic levels. And I'll show you the geology of those reservoirs on the next slide. But here I wanted to show you in map view what these operations look like. So shallow injection is yellow, deep injection is purple. And these are not really depth ranges. When we say shallow, it doesn't mean a certain number, and deep doesn't mean a greater depth number. It means relative to the producing shale intervals. And so shallow is between the shales and the ground surface. Deep is between the shales and basement rock, that crystalline bedrock underpinning the basin. You can see in the Midland Basin, these two operations overprint in most of the areas. In the Delaware Basin, there's a regulatory impact here on our map. So you can see the Texas-New Mexico state line. If you can see my cursor, let me see if I can get a laser here. If you can see my cursor here, so this is the southeastern corner of New Mexico. The rest of the basin is Texas. So you can see that New Mexico permits mainly deep injection. Texas permits mainly shallow injection. So there's this regulatory footprint. Due to correlative rights, which means you can't impact anyone's production in New Mexico, shallow injection has not been permitted to great degrees since about 2010 or so. In fact, 3 million barrels a day of water are moved across the state line from New Mexico into Texas for disposal. You can see that deep injection has plateaued at about 50 million barrels a month in both basins. Shallow injection is going up, and in some cases going up nearly exponentially. So it's increased to about 300 million barrels a month in the Delaware Basin and over 100 million barrels a month in the Midland Basin. So what we're seeing is that shallow injection is taking up the increase in produced water that we see throughout the Permian Basin region. So what are the types of rocks that we are talking about in this basin? Production is coming mainly from these shales, the tight oil reservoirs that have to be fracked to produce fluids, and we won't talk about those today. We'll just talk about the injection reservoirs. So this deep injection above basement is into carbonates mainly, so deep saline aquifers, Ordovician, Siluro-Devonian age, sitting above basement. And so almost all across the entirety of the basin, these are carbonate strata, so in some cases heavily dolomitized, fractured, karsted, and have a great deal of heterogeneity. The shallow injection reservoirs in the Midland Basin are mixed carbonate and siliciclastic reservoirs of Guadalupean age, late Permian. And in the Delaware Basin, these are sandstones, deep water turbidite sands. And I'll talk a little bit later about our injection reservoirs more broadly. So what do these operations look like when we look at the basin as a whole? Here we're projecting everything that's happening in the basin apart from conventional production onto one east-west section line. And so I want you to see deep injection here in purple, our interpretation of the top of basement strata, that's the red dashed line. So you can see that uplifted central basin platform I showed you earlier, separating the two subbasins. Earthquakes are falling almost exclusively in crystalline basement, apart from this set of earthquakes that's in the southern Delaware Basin, which sits in the sedimentary section almost exclusively. And then shallow injection here in yellow between shales and the ground surface. So we have these operations kind of overprinting one another in depth in every given area. So with deep injection, the main concern is seismicity. This is not a concern we've just seen in Texas. In fact, Oklahoma and many other cases, many other areas have had an increase in seismicity associated with deep injection into saline aquifers. If you're familiar with a paper by my colleagues and collaborators, Mark Zobak and Peter Hennings, last year, they published a nice summary of the implications of this type of deep injection for carbon capture and sequestration, or CCS, for class 6 injection broadly. So in Texas, we see earthquakes in many different geologic habitats. We see them on passive margins down here, kind of on the Gulf Coast basins. We see them in foreland basins, such as the Fort Worth Basin, which is where Texas's seismicity really kicked off. Earthquakes associated with deep injection. And then, of course, in the Permian Basin, which makes up the vast majority of recent seismicity across the state of Texas. And that's one of the reasons it's been the focus of our study. So earthquakes are occurring in a range of geologic habitats, mainly associated with deep injection above basement. When we split out those earthquakes into basins, we can see that the Delaware Basin and Midland Basin, as I just mentioned, are making up most of that seismicity. You can see a decrease in earthquake rates through 2025, but we've seen a tick back up in late 2025 and into 2026. So the first thing that we do in my research group when we want to understand the risks posed by earthquakes or the risks of earthquakes is faults. And the state seismologist in Texas, Aaron Velasco, famously says you can't have earthquakes without faults. So fault mapping, characterization, and hazard characterization is one of the key parts of our research portfolio. And I wanted to show you here this example fault interpretation by my colleague Lily Horn for the Permian Basin. And you can see all of these basement-rooted faults mapped as these thin black lines. Areas where we have 3D seismic are in yellow, and there the fault interpretations are much more robust. We have a higher degree of confidence in the faults. In general, we see two distinct fault sets in the Delaware Basin, just one in the Midland, but the dominant fault set that forms the basin structure are these basement-rooted faults that were initially formed as reverse faults, although they're now slipping in a normal and strike slip sense in present-day stress fields. And those deep basement-rooted faults, importantly, extend into the deep injection strata. So there's direct hydrogeologic connectivity between the domain where we see earthquakes and the domain where we see injection. I'll stay on this slide for a second. One of the other things that we found very useful in mapping faults in these producing basins is tracking subtle changes in the depth of horizontal wells. And so as operators are drilling horizontal wells and tracking deviation surveys, they're staying in zone. And there are subtle changes to the depth of the formation due to differential compaction sitting as those formations are deposited above these structural features. And so it's very useful for us for delineating fault zones to look at these modern wells that have been drilled. Once we have a fault interpretation, we use a range of methods to understand the hazard posed by those faults. This is an example of a 2D fault slip potential hazard assessment. We also do this in 3D stress using fault segments on triangulated surfaces, but this is kind of our first pass. How risky are these particular faults given our modern present day stress state? And so now all of these segments are shaded by what we call DFSP, which is the deterministic fault slip potential. What's the pore pressure change required to push them to slip? And you can see in some areas, such as this area of the Midland Basin, these faults are pretty sensitive, and we also have had earthquakes. So we have a nice match here between faults that we might have expected to slip under small pressure changes and faults that have slipped and made earthquakes. We also have areas that are a little bit more challenging to interpret, and such as this area, which is the North Culberson Reeves seismic response area, or the Culberson Mentone earthquake system. And I'll talk a bit more about that in a few minutes. And this system has a lot of faults that don't look particularly sensitive under our current characterization and our current understanding of those faults, given the present day stress fields. So there's a bit of a conundrum here to understand why we have earthquakes where we do in this system. And in fact, this area is one of the most induced seismically active regions in the entirety of the world. So it's a great area for us to study with a lot of available data and a lot of seismicity. In parallel, we work up a geologic characterization of our injection strata in the same way that anyone would for a site characterization, using well data, mapping formation depths and thicknesses, porosities, permeabilities, log interpretations, calibrated to core data, and we build up 3D geocellular models. So I won't spend a lot of time on this, but one thing that I want to note on this plot on the bottom, which is a porosity permeability cross plot, one thing that you can see in these carbonate rocks is that at very low porosities, we have a wide range, in fact, 4 orders of magnitude of possible permeabilities, meaning that we have a permeability system that's enhanced by fractures and faults that govern our flow in these systems in a way that's actually quite challenging to characterize. We can't easily from logs predict permeability in the system, even if we have good characterization of porosity. And so one of the ways that we work around this in our regional pressure models is to calibrate the permeability of our pressure models to achieve a fit between injectivity from downhole or surface pressure, injection pressure data to the model results itself. So we're actually using injection data to kind of back calculate permeability in these dynamic systems. So we use our geologic characterization effort to model pore pressure change with injection. And I wanted to show you an animation here that I hope will work in this. Maybe I have to come out of laser pointer here. We'll find out. Maybe I can just go next slide and see. Okay, so here we show pressure change in PSI for every year. You can see the year ticking along in the top, the pressure building up in this system, and we see the onset of seismicity. I mentioned before that we have these cases where earthquakes and faults sit very nicely over one another in the Midland Basin, and then we have this complex case in the Delaware Basin where earthquakes are sitting quite far from our deep injection wells in some cases. And so when we summarize that, I wanted to put up just one map here to show you what this looks like. So we interpret in the Midland Basin proximal deep injection, broad pore pressure increase of 500 psi or more that's acting on basement-rooted faults that provide this direct connectivity and are sensitive. This is a pretty straightforward, characterizable, and understandable case. And then we have systems like this Culberson-Mentone earthquake system where the pressure plume coming from the north is a bit distal. The faults must be more sensitive than we currently have them characterized as, and or there must be anisotropy in the system that we can't characterize in our kind of radial flow models. And then we have these earthquakes shallower in the southern Delaware Basin. I won't talk much more about them, but they are not associated strongly with deep injection. They're associated with hydraulic fracturing and shallow injection. And so I want to spend just a couple minutes talking about this earthquake system that I think gives us kind of the nicest data set to understand deep injection induced seismicity. Here we've done a deeper dive with the help of the Railroad Commission in Texas. We were able to license some beautiful 3D seismic data that images the basement. This is data from Fairfield Geotechnologies, where we can map out more than two distinct fault sets, in fact, several distinct fault sets, including intra-basement faults that represent this very, very old plate boundary, essentially, the Grenville front, and that seems to be a zone of crustal weakness. And those faults in some cases are linked to basement-rooted faults that extend into the deep injection intervals. And then we have a distinct set of shallow strata-bound faults that are much younger, associated with basin and range extension. And these are the faults that are hosting some of the shallow earthquakes. So we actually have a very structurally and geomechanically complex system here. And then on top of that, we have the fact that the earthquakes themselves, when we look at focal mechanisms and fault plane solutions from focal mechanism data, what we see, and from planes fit to high resolution or high precision earthquake catalogs, we see that those earthquakes seem to be occurring on very steeply dipping faults that are mismatched from the shallower, pretty stable thrust faults that we observe in the basement. And so there's a fault set here that is not easily identifiable in 3D seismic, even when the basement is well imaged. So here are a few of our findings here, and we've written a couple of papers that are in review, but and too much to cover here. I want to move on soon to the next section. But a few findings here that we do see direct kinematic fault connectivity from deep injection strata to basement. Some of our new research shows that there are extraordinarily high diffusivities in these carbonates subject to injection on the order of 65 meters squared per second. And those values are interpreted from pulse pressure tests where operators inject into one well and kind of pulse a well and measure pressure in another well. And so that's the best fit range is anywhere from 20 to 60 meters squared per second. It's an order of magnitude higher than we would have thought. And then from looking at diffusion fronts along earthquakes, we can see a lower but still appreciable along fault diffusivity with migration from injection strata into basement itself. On top of that, we see where these rocks outcrop in the field in far west Texas, that they have talc and phyllosilicate fault cores, which have very, very low mu. So these are much, much weaker potentially seismogenic faults. The assumption in most of these analyses is that faults have a mu of about 0.6, so maybe we need to drop that down to a much, much lower, much weaker fault observation. Okay, so what's happened in this area? Well, regulators both in Texas and New Mexico have taken action for seismicity to varying degrees. And in some cases, operators have curtailed their operations willingly. And so what we saw in 2024 into 2025 is that pressure is coming down in these seismic response areas as operators have backed off of deep injection. And the North Culberson Reeves seismic response area specifically, 20 deep injection wells were shut in here. This is a pretty catastrophic thing for operators. given that the capital losses associated with that injection operation were probably on the order of hundreds of millions of dollars, and those are wells that were dependent on for injection capacity. And so it's a pretty colossal loss of optionality for injection operators in that region. And some of these deep injection wells are 15 or 20 kilometers from any from the earthquakes that have been caused by these deep injection operations. And so there's a bit of a challenge there with this long distance triggering of seismicity. This just shows these earthquake rates coming down in response to deep injection rates coming down. But I want to move on now to the last section so I can leave a bit of time for questions. And that is that earthquake rates have come down beautifully in response to actions by regulators and operators, but injection has continued to go up. Most of that injection now, as I said, is going into shallow reservoirs. And so the demand for injection is now going into this different stratigraphic injection reservoir. And that's posing a new challenge. And it's not really seismicity, although we do have some shallow earthquakes sitting above basement in the southern Delaware Basin I mentioned earlier. Those earthquake rates are very low, and the magnitudes are also low given the types of faults those earthquakes occur on. So they're shallower, stratabound faults. They're not as big as these deep basement-rooted faults. They don't seem to have the potential to host large magnitude events. And on top of that, at relatively minor deep injection rates, we saw very high earthquake rates, whereas in the shallow system, we are seeing very high injection rates with relatively low earthquake rates. And again, that's because these systems are not intersecting, this injection is not intersecting these deep basement-rooted faults that the deep injection system is. But the challenge is a different one, and it's about legacy wells. We go through the same process of geologic characterization and pore pressure modeling as I showed you for the deep system. And so here, showing you snapshots of a couple of our publications on the shallow injection systems. In the Midland Basin, as I mentioned, these are still carbonates, so we have the same challenge in predicting permeability at the regional scale. The sandstones, the siliciclastic injection strata, are much more understandable and predictable and modelable with this very nice linear in semi-log space porosity permeability relationship. So when we look at the pressure buildup in shallow injection, instead of talking about earthquakes, we're now showing surface flows from orphaned and abandoned wells. These are wells that the regulatory agency has to deal with. And so I'm going to try to play this here if I can. Maybe I have to come out of laser yet again. Okay, this one doesn't seem to work, so I'm going to jump to just the 2D final answer here. But to show you how pressure has built up in these shallow systems, and particularly in the Delaware Basin and right across on the Texas side of that Texas-New Mexico state line, where volumes of water are being injected in a much more concentrated fashion. And so you can see that in this region where we've had the strongest pressure buildup, we've had many of these surface flows from legacy wells. I should say there has been pressure buildup on the Central Basin Platform. Our group is working to model that now in this system from surface to basement, but we haven't modeled it yet. And then we have areas where we have relatively little pressure buildup, but we have a legacy well hazard challenge. And so I'll talk a bit more about that for the next 5 minutes. I wanted to show you these north to south cross sections across the basins, similar to the one I showed before, but here for each of the two basins, showing you more of a focus on the shallower injection activity. And so in the Delaware Basin, you can see these deep wells that were curtailed, the very concentrated shallow injection, and that shallow injection reservoir is targeting, or is the same reservoir that was produced from for many, many decades. So the same reservoir properties that made for a good producing well now makes for a good injection well. And so we have overprinting of these legacy and modern day operations. And you can see the well TDs in tiny black dots of pre-1980 vertical wells, which really shows that potential connectivity here. And so this population of wells was completed to enable reservoir connectivity, meaning if they're not now plugged and cased to modern day standards, they serve as potential conduits of fluid through groundwater resources and to the ground surface itself. So let's talk about these legacy wells for just the last couple of minutes here. There are over 250,000 of them across the Permian Basin region. Many of them are aging and are of a vintage that had very different casing standards, cement jobs, and have potentially been exposed to corrosive fluids over many decades. And so we think about things like, 1920s, 30s, 40s, 50s, even 60s and 70s as this population of wells, and many of them are sitting in the shallow. When I say shallow, I mean like a mile deep or shallower, so these upper few thousand feet, shallow reservoirs intersecting with modern day shallow injection. And so historically, many people look at legacy well risk by looking at well density and well age, and we've done that, and that represents kind of one hazard. What is existing anthropogenically in the ground today? What my group does is then layer that with what have we seen in terms of pressurization from shallow injection to date. And here you can see the percent increase in reservoir pressure at the basin scale due to shallow injection. And so when we layer those two things together, we can get an assessment, a qualitative assessment of risk to legacy wells that combines the density and the age of wells and the pressurization from shallow injection. Now, obviously this is a simplified case. There's a lot of work left to do here to look at these legacy wells and look in a bit more detail at their casing records, their cement jobs, all these kinds of things. And so this is a simple first pass. But what I want to show you then is how this qualitative risk map layers with shallow or near surface incidents. These are flows from legacy wells, from orphaned and abandoned wells, or these are drilling challenges that operators face today, or present day well blowouts, geysers, things like that. And so you can see that these fall in a few different areas. Eastern Shelf, mainly because of legacy well density, Central Basin Platform, legacy fields, and present shallow injection pressurization. And then we have this case on the Central Basin Platform that's quite interesting, where regulators have been dealing with many, many issues. And here we have done some work on the caprock quality. And so the map on the right shows the thickness of the evaporite topsoil. This is a beautifully layered anhydrite halite succession, but in some areas it has been dissolved over geologic time. And so instead of a nice competent caprock, we have more of an anhydrite breccia with dissolution pathways and fractures and permeability that you don't have when you have this beautifully layered halite and anhydrite. And you can see that many of these legacy well issues fall in areas where we would say are high or moderate dissolution zones and have relatively thin caprock. And so, yeah, that shows that. So I want to just talk 1 second about a tool that we are employing very heavily to look at the risk posed by injection, and that's ground surface deformation. So in this part of the Permian Basin, or the Permian Basin region of West Texas and New Mexico, a Sentinel satellite takes passes over the region every 12 days or so, and takes a measurement of the line of sight distance to the ground surface. And as the ground surface goes up or goes down, that distance changes, and we can infer then vertical deformation patterns or surface deformation. In the map on the right, we're showing just a 7-year period here. You can see in these basins, they're mainly purple. That's subsidence associated with production of fluids from shale reservoirs and groundwater production to a lesser degree. But then we have areas like this area where we had strong pressure increase with shallow injection, where there's been so much injection that the signal overcomes the subsidence signal and causes the ground surface to actually be uplifting. And so this is one region where we see broad diffuse uplift associated with shallow injection. And that also is where we see many of these issues with legacy wells. And then on a finer scale, we have a couple of these areas that are difficult to see, but I'll zoom in on one on the next slide, where we have very strong surface uplift and in some cases containment losses and associated with legacy wells, surface flows, and well blowouts. And these are in some cases corresponding to low overburden pressure. So where we have a lower vertical stress or a lower differential stress between injection and our overburden, we might be more likely to see uplift. We're working now to determine which of these cases are indicative of containment loss. This is a case in particular in Crane County that's been published on by our group and by a group at SMU, where the causal wells associated with the surface uplift are something like 12 miles away from the legacy well blowouts. But if we look at when those blowouts occurred, we can see a precursor uplift signal, particularly for these couple of these uplifts that are associated with a 12-mile distant plume migration. A precursor uplift signal prior to each of those well blowouts. And then we see the ground surface subsiding as that pressure is released. Those wells were then plugged, but the causal agent in terms of injection was not dealt with until later. And so the ground surface began to uplift again, leading to another well blowout a year and a half later, which really highlights firstly the value of using surface deformation to kind of track some of these features, but also the need to deal with the subsurface conditions that lead to them, not just plug the well, but also deal with that underlying pressure plume. Okay, so I do want to stop there so we can have at least a few minutes for questions. You can skip the first section, but there are some broad conclusions on the bottom. One of the conclusions I think is important is that subsurface pore and pressure space is a shared resource. Forget lease lines and state boundaries. The injection capacity is really representative of basin scale injection, and it's finite and it's dynamic. It changes over time. We need to understand faults and stress for seismicity hazard mitigation. Distal triggering remains challenging. Uplift of the ground surface is a useful early warning signal of injection challenges such as loss of containment. And then understanding the risk posed to the surface environment requires integrating legacy well hazard with current operations. So I'll stop there. Carly, feel free to jump in with anything, and I can go to your wrap-up slides whenever you like.
Yeah, thank you so much, Katie. That was
Welcome.
so great. You have so much data to share. It's
Too much.
but it's great to see. And I know that this is a great example of like using data that we already have from other basins as a proxy for understanding Class 6 operations. So I really appreciate you sharing this and
Sure.
a lot to consider.
Yeah.
Okay, so let's look at questions. And if people have questions, you can go to the Q&A and just type them in there. A few have come in already, so I'll kick it off with these. You did talk a lot about faults that weren't readily identifiable on 3D
Yeah.
seismic. So
Yeah.
I guess how much uncertainty is acceptable in Class 6 site characterization, which I know isn't your specialty necessarily,
Yeah.
but or
Yeah.
just maybe UIC site characterization
Yeah.
as a whole.
Yeah. Yeah, it's a great question, and I think it's one that's challenging to put a number on in terms of uncertainty. What I would say is this: site characterization is obviously very, very important, and so it's if you identify faults that seem to be likely to slip in present day stress fields, that's a challenge that needs to be mitigated and considered. I guess what I would like to say that this work shows is that there's an additional layer of uncertainty, which is to say that site characterization on its own is kind of an imperfect strategy. Even in this area where we have a decade of seismicity and we have beautiful 3D seismic data and we have downhole pressure gauge data, it's a little bit challenging for us to understand why and where we see the seismicity that we do. And it's taken years of research to see that. And so rather than what's acceptable, I guess I would say monitoring needs to play another really strong role there, whether that's pressure monitoring for your plume or whether that's microseismic monitoring, to look for some of these faults and features that might be slipping with relatively small magnitudes, as kind of an early warning for seismicity, I think is something that needs to be, considered. And so I guess my thing there is that there is already inherent uncertainty even with the best data in site characterization. So it's important to close this monitoring and characterization loop to the extent possible.
Yeah, I think that's a great point is we can't fully rely only on perfect characterization before a
Yeah,
project starts. So that's why
yeah,
monitoring is so important. Yeah, that's a
yeah,
really great point.
yeah, yeah.
Um, I was really struck to see that some of the earthquakes and the pressure propagation you've seen in the Permian can really have far-reaching impacts. Like I
Yes.
think you said it was over 12 miles or maybe even more. So
Yeah, yeah.
um how might those how maybe going forward and again thinking about class six could we incorporate those into thinking about how we model our AOR? Because I know when
Mm,
you're modeling your AOR, it's a reservoir model built on geologic models. So, and
yeah.
many times, you have to limit that model, otherwise you need a crazy amount of computing power.
Yeah.
So I guess how can we think about other saltwater disposal or other injection in areas where people are developing class six projects?
Right. Yeah, it's a great question and a great point. And so that long distance and very fast pressure transmission, like we're talking, many miles in the order of hours. This is a very, very diffuse high diffusivity system.
Mm-hmm.
So one of the things, I think is understanding the permeability structure of your injection system to the extent possible,
Yeah.
understanding, faults and whether those faults are faults that, serve as permeability corridors, understanding fracture systems and the rates at which those flow, and or are likely to flow. What are those super highways? Because so many of our reservoir models for these rock types rely on, kind of an upscaling of a matrix characterization of the rock volume. Understanding those diffusive super highways is much, much more important than the kind of the broad scale characterization of the reservoir.
Mm-hmm.
In terms of AOR, none of our kind of radial flow models pushed enough pressure to the sensitive faults that we see here, to have caused them to slip. And so our models, are modeled. If one were had done a class six operation here, uh, general models would not have modeled those plumes reaching this system. I think one other thing to consider in this is, anywhere where you have even very deep, very old geologic control. So plate boundaries, this Grenville front that tracks all the way from the Delaware Basin through the Midland Basin up to the Fort Worth Basin, even all along kind of this ancestral plate margin seems to be very sensitive. And you can observe it in or infer it from gravity and magnetics and other data. And those are areas where earthquake corridors are clustering, even with distal injection. And so those are things
Yeah.
to be aware of.
Yeah.
Yeah.
Thank you.
That
Okay,
makes
I
sense.
think we
Sorry.
have time for one more question and then
Sure.
we'll do our wrap-up slide. So
Sure.
this question says, it seems the Permian Basin is nearing the limits of available injection space.
Yep.
Where do you think oil and gas operators will focus their efforts to find new injection sites or horizons or trucking or
Yeah. Right. That's a very salient question. So our work shows that there are areas of the Permian Basin that have already exceeded capacity. And when I talk about capacity, I talk about it in like a responsible class 6 way. I don't mean what will anyone allow you to inject in class 2 injection in Texas or New Mexico, for example. What will the system allow you to safely inject? What's your social license to operate? And so for my view, if you've had a well blowout or surface flow, you've exceeded the capacity of that particular system, given the legacy well hazard, given the sensitivity of faults. So there are areas that are already at capacity in the Permian Basin. And importantly, there are areas also where injection optionality has been lost. That means deep injection has been shut in, shallow injection is the only option. And so operators are very reliant on a diminishing number of options.
Mhm.
What we see in the Permian Basin now is we see large acquisitions of land by land companies who then go in and do massive well plugging campaigns to, hundreds of wells to increase the capacity of their system. We see pipelines being constructed to the Central Basin Platform, which has challenges too, but does seem to have some injection capacity. I think we will probably see a future of out of basin pipelines being constructed. We will also see increasing treatment of water for beneficial use and land application, but those solutions are a bit further off. So for now, it's going to cost more to inject. Regulatory agencies are already requiring more data about the frac gradient of injection intervals, the frac gradient of caprock, things like about legacy wells, larger AORs in class 2. The AORs are not plume based, they're just a set distance
Mhm.
in Texas. And so we're seeing an increase of those to capture some of these or to mitigate some of these issues. It's just going to cost more money to dispose of water. I do think, though, there are some potential class 6 operations in the Permian. What I would say, though, is the competition for pore and pressure space there is very strong.
Yeah.
And, those are areas that are pretty well sealed up for wastewater disposal.
Mhm. Mhm.
So
Well, thank you
good.
again. This really was a wonderful
You're so
proxy
welcome.
just for understanding legacy basins as more basins are looked at for CCS projects. So,
Mhm.
yeah, the last few minutes
Sure.
we'll just wrap it up. So, we have 3 more webinars in our series. They're every other month. So we have one in July, one in September, and one in November. If you scan that QR code, you can get more information and sign up. And then, yeah, that's, I guess, last slide is
Yep.
you can contact me or reach out to Katie if you have any more questions. As I said, we'll share the recording and there's my contact and LinkedIn. And thank you so much, Katie. I appreciate it. And
Thanks.
all of a sudden, an hour has gone by. So,
Amazing. Time flies.
yes,
Thank you so
yes.
much for having me, Carly.
Thank you. Thanks, everyone. Have a great day.